Astronomers have just uncovered evidence of a supermassive black hole inside the Large Magellanic Cloud, LMC, a dwarf galaxy orbiting the Milky Way. Even more astonishing, the LMC is on a long-term collision course with our home galaxy. In this video, we'll break down the science behind this groundbreaking discovery, explore its significance, and look at other famous supermassive black holes that help us understand this cosmic phenomenon. Finding a hidden supermassive black hole in a neighboring galaxy is no easy feat. Unlike stars, black holes emit no visible light. They are, quite literally, invisible. Scientists detect them by observing their gravitational influence on surrounding stars and gas clouds. In this case, researchers employed a brilliant method, tracking hypervelocity stars, stars moving at extremely high speeds. These stars are rare and don't speed through space randomly. Often, they are ejected by a massive, unseen object, such as a black hole, through a process known as the Hill's mechanism. This occurs when a binary star system, two stars orbiting each other, drifts too close to a supermassive black hole. The intense gravity rips the system apart, capturing one star while slingshotting the other away at extreme velocity. Using data from the Gaia Space Telescope, which precisely maps the motions of billions of stars, scientists discovered that 9 hypervelocity stars in the Milky Way originated from the Large Magellanic Cloud. This was a crucial clue. These stars shouldn't be moving so fast unless something extremely massive ejected them. After extensive analysis, astronomers concluded that the culprit was likely a supermassive black hole, estimated to be around 600,000 times the mass of our Sun. This finding is groundbreaking because it confirms the presence of a supermassive black hole at the core of the LMC, something that was previously uncertain. It also fills a critical gap in our understanding of black hole formation and growth. We know of small stellar mass black holes, which form from collapsing stars, and typically have masses a few to tens of times that of the Sun. We also know of enormous supermassive black holes, millions to billions of times the Sun's mass, such as Sagittarius A at the center of the Milky Way asterisk. However, black holes in the middle range, like this one, are much rarer and harder to detect. If confirmed, this discovery could shed light on how black holes evolve. Do intermediate black holes grow by consuming gas and stars, or do they merge with other black holes during galactic collisions? Answering these questions will be crucial to understanding the cosmic life cycle of black holes. The collision course. What happens when galaxies merge? The Large Magellanic Cloud has been orbiting the Milky Way for billions of years. But it's not just a peaceful satellite, it's actually falling toward us. Astronomers predict that in about 2.4 billion years, the LMC will collide with the Milky Way, causing dramatic changes in our galaxy's structure. The fate of the LMC's black hole. When the LMC merges with the Milky Way, its supermassive black hole won't just disappear. It will gradually sink toward the center of our galaxy, pulled by the immense force of gravity. Over millions of years, it will get closer to Sagittarius A*, the existing supermassive black hole at the heart of the Milky Way. As the two black holes approach each other, they will begin to orbit one another, forming a binary black hole system. Over time, gravitational waves, ripples in spacetime predicted by Einstein, will carry away energy, causing the black holes to spiral inward until they merge in a cataclysmic event. Such mergers have already been observed in smaller black holes, using gravitational wave detectors like LIGO and Virgo, but witnessing one within our own galaxy would be a once-in-a-lifetime event. Other galactic consequences. Beyond the black hole merger, the collision of the LMC with the Milky Way will reshape our galaxy in other ways, triggering new waves of star formation as the LMC's gas and dust interact with the Milky Way, potentially altering the structure of our galaxy, making it more elliptical instead of its current spiral shape. Serving as a preview of an even larger cosmic event, the future collision between the Milky Way and the Andromeda Galaxy, expected in 4.5 billion years. Other famous supermassive black holes and what they teach us. To better understand the LMC's black hole, we can look at other well-known supermassive black holes across the universe. Sagittarius A*, the black hole at the center of the Milky Way, discovered due to its gravitational pull on nearby stars, which orbit it at extreme speeds. In 2022, the Event Horizon Telescope captured the first ever image of Sagittarius A*, confirming its existence. Messier 87, M87, a colossal supermassive black hole at the center of the giant elliptical galaxy M87, estimated to be 6.5 billion times the Sun's mass. In 2019, it became the first black hole ever imaged, showing a glowing ring of light surrounding a dark center. 10618, one of the largest known black holes, estimated to be over 40 billion solar masses, located in a quasar, an extremely bright and active galaxy, where it devours surrounding gas, producing massive jets of energy. What these black holes reveal. These examples show that black holes don't remain static, they grow over time by consuming nearby material, or merging with other black holes. If the LMC's black hole merges with Sagittarius A*, it could trigger even more growth, potentially making it as massive as M87's black hole over billions of years. The discovery of a supermassive black hole in the Large Magellanic Cloud adds a crucial piece to the puzzle of galaxy evolution. As we watch the slow-motion dance of galaxies over billions of years, we are reminded of how dynamic and ever-changing the universe truly is. If you enjoyed this deep dive into the cosmos, don't forget to like, subscribe, and hit the notification bell for more mind-blowing space discoveries. See you next time.